controller braces an interrupt. Then the device driver initiates the I/O. After the I/O is initiated, we come to know the status and hands it to the interrupt handler of the CPU. Then the CPU resumes the processing of the interrupted task and the cycle continues. DMA or direct memory access. It's when there is a large movement of data. The CPU cannot process one byte at a time as it is time consuming. That's where the DMA comes. It is a special processor which bypasses the CPU to transfer data directly between I/O device and memory. The host issues the following commands to the DMA like source and destination addresses, read or write mode, count of the number of bytes, writes location of command block to DMA controller, bus mastering of DMA controller which grabs bus from CPU and when it's done, interrupts to signal completion. There is one more approach called the DVMA, which means direct virtual memory access. The difference of DVMA to DMA is that it uses virtual address instead of physical address. We have here the six-step process to perform direct memory address. Step 1, the device driver is told to transfer this data to buffer at address X. Step 2, device driver tells this controller to transfer C bytes from this to buffer at address X. Step 3, this controller initiates DMA transfer. This 4, this controller sends each byte to DMA controller. Step 5, DMA controller transfers bytes to buffer X, increasing memory address and decreasing C until C is equals to 0. When C is equals to 0, DMA interrupts CPU to signal transfer completion. Next is the block and character devices. Blocks are devices which access blocks of data. For example, is the bus drivers and CD-ROMs. In such type of devices, we can access raw I/O, direct I/O, or file systems, which use commands include open, read, write, etc. Character device which handles single character at a time. For example, is keyboard and a mouse, in which we can pass a single character by a click and we use command like get, put, etc. Network devices. In network devices are quite different from block and character devices. This mainly includes a software interface. This separate network protocol from network operation. This also includes select functionality. The approach in network device vary widely from block and character devices like pipes, FIFOs, stream, and queues. Next is the clock and timers. There are three types of time services which are commonly needed in modern systems nowadays. Namely, get the current time update, get the elapsed time since the previous event, and set a timer to trigger event. Unfortunately, time operations are not standard across all systems. A programmable interrupt timer, or what we call PIT, can be used to trigger operations and to measure elapsed time. And on most systems, the system clock is implemented by counting the interrupts which generated by the PIT. Next is the kernel input-output subsystems. I/O scheduling. I/O scheduling can requests greatly improve overall efficiently. Priorities can also play a part in request scheduling. Buffering and caching can also help and allow more scheduling options. Next is buffering. It is a process where it stores data in a memory while transferring. Slow devices may write data into a buffer, and if the buffer is cold, the entire buffer is sent to the fast device all at once. The buffering helps to cope with the device speed mismatch, and to cope device transfer size mismatch, and to maintain copy semantics. This slow device still has somewhere to write while this is going on. A second buffer is used, and two buffers alternate as each becomes full. This act is called double buffering. Next is caching. It involves keeping a copy of data in a faster access location than where the data is actually stored. Buffering and caching are very similar, except that a buffer holds the only copy of the given data item, where a cache holds a copy of the data stored elsewhere. Buffering and caching go hand in hand, and open the same storage base may be used for both purposes. Next is the spooling. Spool means simultaneous peripheral operations online. So, a spool buffers data such as the printers that cannot support internal data streams. Spool queues can be general or specific. Operating system can also provide support for processors to request or get exclusive access to get the particular device and to wait until the following device is available. Next, we have here the life cycle of an I/O request. Next, streams. Streams mechanism provide a bidirectional between a user process and the device drivers, in which the device interacts with driver end and the user process interacts in stream hand. Streams are widely used in Unix. Each module has a read queue and write queue. Flow control can be optionally supported, in which case each module will buffer data until the adjusted module is ready to receive it. Without flow control, data is passed along as soon as it is ready. User process communicate with the stream head using either read and write or put message and get message for message passing. Stream's I/O is asynchronous, except for the interface between the user process and the stream head. Performance. The I/O system is a major factor in overall performance and can place a heavy loads on other major components of the system. Interrupt handling can be relatively expensive, which causes program I/O to be faster than the interrupt given I/O when the time spent busy waiting is not existed. Network traffic can also put a heavy load on the system. Consider for the following example the sequence of the events that occur when a single character is typed simultaneously. Improving performance. Improving performance in order to uh, improve the performance in the operating system, a few changes can be made in the I/O system, namely reduce number of context switches, reduce data copying, reduce interrupts by using large transfers, smart controllers, and polling. You can use DMA, you can use smarter hardware devices. We need to balance our CPU, our memory, our buses, our input-output performance for highest throughput. And we can move user mode process daemons to kernel threads. And that's it. Thank you for listening.